Welcome to tutorial 3. I'm hoping to do a few examples of things related to diodes and op-amps that we've seen most recently today. And again, please feel free to stop me at any point and ask questions. Hopefully this can be quite interactive. Okay, so I figured because we started talking about op-amps yesterday, maybe it's better to start with op-amps now, that hopefully they're fresh on your mind, and then we'll do something related to diodes later on. Okay, so maybe a quick review of the op-amp would be a good idea, and in particular the ideal op-amp. Let me just draw it here. Recall that the op-amp was an active device and needed to be powered up, so it has its connections to power supplies on the positive and negative sides. But very often we don't show those explicitly, but it's important to keep in mind that they are there. But the main terminals are the two inputs, the inverting and the non-inverting input, and then the output. So call these V1, V2, and Vout. Now the op-amp is a complex device, and to actually exactly describe a real op-amp, there's a number of parameters. But one of the great things about op-amps is that they have this property of having a very, very high gain. And that makes it possible to build a large number of circuits around them where the op-amp gain itself has, as long as it's very large, has very little effect. So most things are determined by everything else around the op-amp. And so that's why the ideal op-amp model is a very useful one. And especially, again, if you want to gain insight into how the circuit works and design things, it's very useful to start with an ideal op-amp model for things. So we are going to do a couple of examples with ideal op-amps. And again, if I don't specify explicitly, I mean an ideal op-amp is what we're using. And then we'll also look at later on what happens if if you want to bring in some real aspects. But for now, assume there's an ideal op-amp, and the ideal op-amp has this property that its gain is infinity, and its input resistance is infinity, and its output resistance is 0. Input resistance being infinity means there is no current going through these. So these two currents are 0 for the ideal op-amp because the input resistance is infinitely high. The output current is what? Can be anything, right? Because remember, the output current comes from this internal thing that we modeled with a voltage-controlled voltage source as an ideal voltage source, which can provide any current. Okay? Of course, in a real op-amp, there are limits. But in an ideal op-amp where this output resistance is 0, so it's a short circuit there, there is no voltage drop internally regardless of what current you're pulling, and so there's no limit on the current. And the current can be either way. Okay? So I'm not going to show this explicitly, but can be anything. Again, notice this is for the ideal op-amp. And the gain is infinity. So Vout, which is this, will be infinity if there is even a tiny voltage drop between the two inputs. Conversely, if you build a circuit to keep the op-amp within a range where there is no, where the output is not going to tend toward infinity, meaning that it won't get stuck at one of the power supply levels, it won't saturate, then it will require that the voltage difference between the two inputs be 0. So let me write that down. If we manage to keep the opamp within the linear region of the characteristics, so away from saturation, then V out is a finite value. And of course, V out is always going to be a finite value, but you're also staying within the linear region, so that relationship holds. So you can conclude that the difference between these two inputs is 0. And so whatever voltage you see on one side of the op-amp, on one of those two inputs, will be replicated on the other side, on the other input, without the two being physically connected. In fact, inside the op-amp, there's an open circuit there, right? They're not connected internally. That's very important to keep in mind. And so if you analyze a circuit where you know that the op-amp is going to be kept within the linear region of the characteristics, then you know that the two inputs are going to be at the same potential. And that's really a key point of analyzing op-amp circuits. Now, if you had a real op-amp, of course, A is not infinity, so the difference between the two inputs is very, very small. But very often, this tends to be a good approximation for a real op-amp. So we saw a number of op-amp circuits. And what I'd like to do now is to just do a couple of examples of putting some of these things that we've learned together. So consider this circuit. Okay. So try this on your own. Calculate V out as a function of V1 and V2. if these are ideal op-amps, and if we trust that the circuit has been built such that the op-amp stays within the linear region. And by the way, if I express that as an assumption, maybe it's something that you should question, right? I haven't discussed yet the justification for that statement or that assumption, right? I keep saying, well, let's assume that it stays within its linear region of operation. So I invite you guys to think about it at home. And we will talk about it tomorrow maybe. But let's assume for now that we stay there. Well, again, you can write all the equations, but like the kind of things that we saw yesterday, let's start by putting down whatever we know. So this is 0 volts here, which then gets transferred to other pins because the two inputs should not have a voltage difference. And in fact, same here. Okay. And we know that the op-amp does not draw any input current, so we have 0, 0, 0. And then we can start solving things directly on the circuit. And you can write them down also, but I'll see how much I can fit on the circuit directly. So across this 2 kilo ohm resistor, we have this current, which is V1 minus 0 divided by 2 kilo ohms, right? And then the same current will, by KCL, will go here. So that will allow you to calculate this voltage. And this voltage would be the voltage on this side, which is 0, minus 4K times V1 by 2K. So that's minus 4 by 2 times V1. Now, we have the same situation on this side, so we have V2 over 5K here, which will go through here. And so here we'll have minus one over 5 V2. What do I do next? This is correct. What's next? So I have I1 going here. And can I say that this goes this way? Who says I can? Who says I can? No? Can? Can't? No, can't. Who says I can say that this current will continue along the path that I've indicated? I can? Who says I can't? I cannot. You're very, we have mixed feelings about this here. Well, I can't because the output of the op-amp could have a current, right? Look at that. The output of the op-amp can have any current. So it's one of those places where people make a lot of mistakes. So don't make that mistake. There's no reason to assume that the same current will go that way. So that's one thing. And the same for the other one. I cannot. So what can I say? What should my next step be? Which voltage difference do I know?
Between the 2 points you just calculated.
The inputs?
Well, like 4 over 2 V1 and 1 over 5 V2.
What about those values?
Difference will be the input to the.
So here I have a suggestion. The difference between minus 4 over 2 V1 and minus 1 over 5 V2 is going to be the input to the next stage. Who agrees with that? Who disagrees with that? I also disagree. So what should I do next? You're troubled by something.
Yes.
I can't help. So am I. Think about this, guys. What's happening here? You made one very good observation here. You said this is all one node, right? It's just wires. So what did I do there? Let's say if we label this the output of the first op-amp circuit, the top left part, this over the input, being this, is the ratio of those resistances with a negative sign, which is what we got here with this analysis, right? So the first op-amp just made it so that the input, the negative input is also at 0 volts, which then sent that V1 over 2K current down the first resistor, and then the same current was forced down the top left resistor, 4K. And the voltage drop then across the 4K determined what the output should be. And that basically gave us what we also saw yesterday in an inverting, basic inverting configuration, right? So that gave us minus V1 times 4 over 2. And I did the same exercise. And you saw that I didn't need to memorize that formula. It was very quick to do the analysis. And I got minus 1 over 5 V2 for the output of the second op-amp. But these are connected to the same node. Anything that troubles you guys? I know there's something that troubles you. What have I done? Well, so let's put numbers. V1 and V2 are two independent numbers here, independent inputs. So I'll say V1 equals 5 volts, V2 equals, let's say, 2 volts. So the top number will be minus 10. The bottom one will be minus 2 over 5. What do I make of that? That wire would get really hot. Something in the circuit is not going to be happy. What did I do wrong? Let me ask you another question. If I did this, so I have, if I build something like this, and I ask you what the voltage is at this node. What's the voltage at this node? Yeah. What you guys are telling me, some of you at least, is that maybe I should not do this. Now this you see readily, because if I say, well, I have a 1.5 volt battery and a 9 volt battery, and I will ground one end of the negative side of both of them, and the other side I'll connect. You will say, well, I had better use a wire that's so long that has a very high resistance, right? Otherwise, I'm putting a huge conflict between the two batteries. If it's really a good wire there, it means I have infinite current. Voltage difference over 0 resistance, infinite current. Not good. Okay? What you see up here in this op-amp circuit is not very different. It just looks a little more benign. But you see a conflict there. It's a circuit that should not be built because, and this points to a feature of each of those two op-amp circuits, each of the two individual stages, top left and bottom left. You see that in finding the output of the first one, all I had to do was to look at the circuit built around the first one. It was acting, or wanted to act anyway, independently of the rest of the circuit. And so did the bottom left portion of the circuit. And so if you connect two things that act independently, but at the end you take their outputs and connect them together, is not any better than taking two voltage sources and connecting them together, right? So very bad thing to do here, okay? You can't really solve this because you shouldn't build this circuit to begin with. I mean, the answer is that yes, in this wire, like you said, there would be infinite current. Now, maybe that infinite current runs from this point all the way to this point, or, you know, anyway, something very bad. This highlights something interesting about the circuit. Even though it's got a large number of resistors and a large, well, and three op-amps. So imagine having to write all the KVLs and KCLs for this. Imagine I drew all the wires explicitly, and you had to go around and find all the loops. That could give you a good system of equations with voltages and currents, and you know, something sizable. And you might end up even getting an answer from it by making some mistake somewhere, right? But if you analyze the circuit, you will see that actually you can break it down in two chunks. And this is part of, you might say, the usefulness of these elements, because you can make modules that act essentially individually. And so you can stack things. You can cascade things and build bigger functionalities. But of course, you have to do it the right way. So we know that we've done something wrong here in connecting these two together. But if I didn't have that connection, well, maybe this is OK, right? Now, how can I fix this by turning this into a circuit that's useful, that does something? This? Sorry, where? So here's one suggestion. If I do this, will things be OK? Who says it will be OK? Who says it will not be OK? Why not OK? What kind of objection do you guys have? So what is wrong here? Now, you say the third op-amp doesn't have its plus and minus terminals at the same potential. Why not? Why doesn't it have the terminals at the same potential? I changed the circuit, so maybe I should also change the solution of the previous circuit. Who says it's OK to do this? We have tripled the number of OKs since then, quadrupled. Who says it's not OK? Well, let's see. Let's see if I run into a difficulty, right? So far, I have concluded that at the top, I have minus 2v1. At the bottom, I have minus v2 over 5. So the minus v2 over 5 is all along this node right here, all the way here, which then imposes on the negative input of the third op-amp also minus v2 over 5. I don't see any conflict. I'll have a current going through this resistor that's determined by minus 2v1 on the one hand and minus a fifth of v2 on the other. And that current will then go through the 9 kilo ohm resistor and give me an output voltage. So this is OK. There is no conflict here. Now, this is not the circuit I had in mind, but this is a circuit that at least will not present a problem when you build it. Now, what I had in mind was a different correction, something a little more symmetrical. How about this? Is this OK? Oh, yeah, you can keep that. Who says this is okay? Who says this is not okay? All right, I think we have reached a good point. So now you have a pretty easy problem on hand. So there is the current that you can calculate here. And this current will be minus a fifth of V2 divided by 3K, right? So this is minus V2 divided by 15K. And this current will be minus minus 2V1 divided by 3K. And then what is the current here? It's the sum of these two. They add up to give you this larger current there. And then you get the output here. So if you call this, well, you can write it down here, minus 2/3 of V1 minus 1/15 of V2. And so V out then will be equal to 0 minus 9K times that. Okay, and you can simplify. So maybe minus plus 6V1 plus 3/5 of V2. So that's V. So what I hope this example highlights is, yes?
You didn't put that 3K, like, did you just put it for symmetry?
No. It's I could put any resistor there. So the question is, the second 3K resistor that I added, was its purpose to keep symmetry? And the purpose was not to keep symmetry. The purpose was to not directly connect two nodes on which different voltages have been imposed, right? So I wanted a resistor between those two nodes, so as to avoid that previous contradiction on the circuit, or conflict. I chose the value 3K, you might say arbitrarily, or you might say because I wanted it to be something that 9 can be divided by, or maybe it appeals to one symmetry. This is just an example. So I hope this highlights, one, the fact that you can indeed, that for an op-amp circuit, as much as you can analyze it by writing all the equations completely, you might say mechanically, without trying to understand the circuit, and sometimes that's what you need to do, but very often, and in fact most commonly, that's not a good idea. Most commonly, you want to try to understand what the circuit is doing and break things down. And often op-amp circuits do have this, this property of being, to some degree, modular. Some modules being more or less independent of other modules. Not always, and not for all modules. But that means that you have to try to understand the circuit. And you see, the previous circuit that I had drawn without this resistor, without this 3K resistor that I added at the end, it looked very similar to this, right? And I suspect many of the people who said I can do it in that clicker question had not thought about the conflict. Because it's very tempting to look at a circuit and say, oh, it looks like I have a couple of non-inverting amplifiers, or inverting amplifiers in this case, and I have another thing there maybe that looks like it's adding things, without noticing that there is something seriously wrong, right? So I hope this serves as an example to point out that you have to look at circuits very, very carefully. And if you're going to use things that you know from the past in terms of how each module operates, you have to make sure that those are applicable. And that's not always the case. So I hope this also serves as a warning of looking for things very carefully. OK, so this is one example. Anything you guys would like to discuss here? And please verify, as always, that I've done the math correctly. But at this point, I intended for this to be correct. This is not supposed to have another conflict. OK. So should we do another example? Now solve this circuit. Sorry. Assume that at t equals 0, there is no voltage on the capacitor, no current through the inductor. Or capacitor voltage is 0. So if we call this IL and this VC, IL is 0. Find V of t for t greater than 0. That V is a voltmeter there, right? And if you're concerned about how these relate to the ground of the op-amp, you can assume that this has been grounded. Sorry, I noticed I had one mistake here that I didn't want to make. This wasn't intentional. This was just a plus minus sign. I had put in the wrong order.
This like first circuit here when I had it connected there.
Mm-hmm. So let's see. Well, it's maybe a little bit of a more complex circuit. But we shouldn't have any fear. We have the laws of circuits, KVLs and KCLs. Right? So I can write those and all the element relationships. And I can try to navigate my way through those that system of equations. But like I said, again, with op-amp circuits, it's normally a good idea to try to get a sense of what's happening before launching into something very mechanical. So what is happening here? Well, first of all, I have included that voltmeter. What kind of complication does that add to the problem? What does the inclusion of a voltmeter in the problem add in terms of complexity? What would the difference be between this and this? What's the difference between this circuit and the previous one? No difference. Okay, so that's good. The voltmeter has infinite resistance, ideal voltmeter, so it's not drawing any current there. It's just measuring that voltage difference. It's the same problem. Okay, what can we say then? Let's see if we can simplify things on the circuit before starting to write equations. So this is my ground, and here I have VI at this node. This is all one node, as you guys identified. So if I have V here, which is my question, and what's the thing that the voltmeter is measuring? Well, this is V all the way. So this is V here. what's the next thing that I can say? Sorry, say again? V is either 0 or infinite. Is that what you're saying? And why is that? Now, the output of the op-amp, why should it be either 0 or infinite? Now, so we have a suggestion here. It says, well, I have connected the output of the op-amp to one of its inputs. So it has to be either 0 or infinity. Who agrees with that? Who disagrees? Why do you disagree? OK. That's a good answer. Well, what can I say about this node? Some say it should be V. Why is that? Assuming that the op-amp is doing its job in the linear mode, and if it has infinite gain, if its output is finite, there should be no voltage difference between the two input points, right? So if I have V at the inverting input, I should also have V at the non-inverting input. So the voltage difference between the two inputs of the op-amp is 0, right? But it doesn't mean that each pin should be 0. Where will it be 0? But why does the output have to be 0? You see, the difference between the two inputs is 0, but that multiplied by infinity will give you a finite output. Okay, so there is no contradiction there. So all this circuit is telling me, at least at first glance, right? Maybe later on I'll discover that there is something horribly wrong and things will be infinity or something. We haven't completed the analysis yet. But at first glance, giving it the benefit of the doubt, all it's suggesting is that, well, I have V all the way here, and the op-amp will simply virtually connect the two inputs. Again, they're not hardwired, but they will they will mirror each other. So if I have V on the non-inverting input, I'll also have, sorry, if I have V on the inverting input, I'll also have V on the non-inverting input. And so far, everything is happy. There's no voltage difference between the two inputs, and the output is a finite value. OK? At the input, I have 0 voltage difference. Multiplied by infinity, the op-amp open loop gain will give me a finite value V at the output. So let's continue the analysis. What's the next thing I can say? Well, let's just start writing things down. First of all, the op-amp will have 0 input current. 0 amp, 0 amp. So that simplifies things. I'll make a few observations and write down equations. And I'm doing this, you might say, more or less in the spirit of nodal analysis. So I have a node voltage here, Vi, another node voltage here. Let's call it V1, maybe. Yeah. I have V here and here, so that's all written out. And I think I have all the node voltages. So let me start writing things down. For instance, this current, if I call this I1, I know that Vi minus V1 is simply R1 I1, right? What is this current? It's the same as IL, right? Because there is no current going through the input of the op-amp. So the current going through R2 is the same as IL. So I can also say, for instance, V1 minus V is R2 IL. What can I say for the inductor? V minus 0, if we call this 0 volt. So big V minus 0 is L dIL by dt. Have I left anything out? Well, the capacitor. We also, if we think about this current of the capacitor, if this is IC, IC is C dVc by dt, right? But Vc itself is V1 minus V. Is there anything I haven't taken into account? The KCL here I haven't written yet. So that would be I1 equals IC plus IL. Anything else that I've left out? I hope not. Let's see. I have taken care of all the node voltages. I have implemented the KCL here and here. And here I have already indicated that I have 0 currents going through the op-amp. So that's good. I have written the element relationships for R1 and R2 and L and C. I think I have included everything. You see? So already the system of equations is smaller, a little less daunting than if you wanted to write everything mechanically by drawing all the loops and all the nodes and writing KVLs and KCLs. Okay, so you might say a nodal analysis type of approach here was easier. Now, I didn't write it formally like nodal analysis, right? I'm allowing myself freedom to write things here. Okay, but next is just to combine these. And it's actually not very difficult. Okay, if you combine these, and I don't know if that's a very good use of time here, but I've tested this problem. If you combine it, you should get a second order differential equation for V. So just go as a practice. So this, let me put it this way. The rest is no different from examples we've done in the past of second order circuits. Okay, assuming that I designed this properly and I did things correctly. So you guys can go verify. Now combine these. And simplify. To see if you can get a second order differential equation for V. It should work. Okay. Don't want to take time now, but do it at home. So although the appearance of the op-amp there might maybe at first introduce some complexity, you see that in effect it's not doing something too crazy, because from the point of view of solving this problem, try to step out a little bit of the page and look at the big picture. In terms of the way the system of equations is working here, okay? Look at all of this. That includes two nodes in there, both of which are at V, right? So in effect, it's as if, from the point of view of your KVLs, it's as if the right-hand side of the capacitor had been connected to the top of the inductor, you see? Because that's V, and the top of the inductor is also V through that op-amp, you see? Now, if I gave you that circuit, and again, the voltmeter, its presence there is just symbolic. It's not imposing anything on the circuit. So imagine the voltmeter was not shown explicitly. And if the top of the right-hand side of the capacitor was connected directly to the top of the inductor, that would be a pretty standard problem, you might say, right, of RLC. Now, I'm not saying this is exactly that, because of course that's not a physical connection there, but they have the same voltage. Okay? Now, maybe there is something a little different there because the current of the capacitor is not going to the node where that R2 and L are. So I'm not saying the two are the same problem. Okay? They are not, because you see, in this case, R2 and L have the same current. If you make the change that I suggested, there will be the capacitor current going between the two. So it will change the solution. But I'm saying from the point of view of the voltage across the capacitor, it looks like that. So there are similarities with that problem. Okay? And so in general, the approach is not very different. But of course, the answer is going to be different. But the way I solved it was very much the same. I implemented everything that I knew about the circuit. But I started by first simplifying as much as I can before launching into a full-blown solution. Okay, so that's what I'm hoping that this will convey to some degree. And so please try it on your own. See if I did it correctly, if you can get a differential equation. And if not, let me know. Okay? So that's a good exercise for home. So maybe this is enough of op-amps for now. We'll continue the discussion on op-amp tomorrow. We'll look at a few other things. But for now, I'd like to also do a little bit more on diodes. So I have this problem. So I want to do a regulator problem using diodes, using a Zener diode. Okay? Consider this circuit. So let's say I have this input and it goes through this resistor. This is 1 kilo ohm. And then here I have a Zener diode. And then a resistor R. And here are my parameters. Vi varies between 10 volts and 20 volts. So it's a variable voltage. Maybe it's a sinusoidal or what have you. It varies between those 2 points. These are its maximum and minimum. The characteristics of the Zener are this. In the Zener mode, in the reverse breakdown mode, this Zener diode can be approximated by a VZ0 of 8 volts and an RZ of 20 ohms. So this is a linear approximation for that Zener diode. Its Zener knee current, IZK, is 1 milliamps, 1 milliamp. And the maximum current it can take is 10 milliamps in reverse, in breakdown. Okay, the maximum current it can handle is 10 milliamps. What range of resistance is acceptable for R? So what is the range that's acceptable for R for this circuit to have a regulated output voltage? All right, let's take a look together. First of all, maybe a brief reminder. If this is the Zener IV characteristics, in general, it looks like a regular diode, except it has this sharp, particularly sharp vertical drop in breakdown, and it's been designed to operate there. And this is what you are representing with a straight line. Okay, and this straight line has these parameters, minus Vz naught here, and then it has the slope one over Rz. All right. So we are saying that under operation, if it is on that line, you can represent it with a simple voltage source and a resistor in series. This is the simpler model, that the approximate model that we described already for the Zener diode. And the requirement for this was that you be somewhere beyond this point. This is what we called the knee current with a negative sign there. Okay, as long as you are here, you're in good shape. Now, you also don't want to exceed, if this line can be extended, but you don't want to exceed the maximum that the diode can handle, because beyond a certain amount of current, the power dissipation will be too much for it, and it will be destroyed. So you want to stay in the highlighted region. Now, if you look at the circuit, the challenge is that the input voltage is varying, in this case between 10 volts and 20 volts. So when is a situation where things are in danger? You want to make sure, first of all, that the Zener current, this Iz, never drops below Izk. Notice that I'm using that direction for Iz. So the current I that I've plotted on this graph is actually this, right? So Iz is minus I. And because I'm working in the reverse breakdown mode, it's why it's conventional to use minus I, which we call Iz in this case. And that's why I have minus Izk and minus Iz max, because Iz is now a positive number. So I want Iz to stay above Izk and below Iz max. Now, as the input varies, when is a point where I have to worry about Iz becoming too low? Is it when is it when Vi is too low or too high? At which point do I risk Iz becoming too low? Well, let's look at it this way. Consider this. Let's call this IR. Okay? And this is Vz, which is what I also have across the load resistor. if I am operating in this Zener mode, in the highlighted region, you notice that the voltage across the diode is more or less constant. It's somewhere around that minus VZ naught. Or VZ is somewhere around VZ naught, plus or minus some variations. But this is a line that's very close to vertical. So you might say the output current is more or less constant. It's not exactly constant, but it varies little. And we will worry about those variations. But for a first order analysis, we know that if we are in the proper mode, IR is not going to change by a huge amount. So my concern really is that I want IZ to be within these limits indicated, and IR something that's not changing a whole lot. Well, so that means then that if I call this IS, as in the source current, that IS, which by KCL at that node, is the sum of IZ and IR. That IS is going to vary more or less the same way that IZ does, because the variations in IR are going to be small. So it's primarily the variations in IZ that will determine the variations in IS. Now, what I have to make sure of is that as VI varies, that IS does not vary to the point that IZ will fall outside the range. So that's my thing. So now let's try to solve it. One, make sure that when VI is at its lowest, IZ is still does not fall below the knee current. Okay? So that's really the limiting condition. So I have to solve the circuit, and realizing that here I have 10 volts at the minimum. Okay. Now if I have 10 volts there, I don't want IZ to be any below IZK. So it means I want IZ to be just at that limit, 1 milliamp. So if I want 1 milliamp here, what will VZ be? Because if I know VZ, then I can calculate IR, and then I am all set. Okay. Now it might be more easy or more convenient to actually represent the circuit with the simplified diode model. So if this is what I had, and this was 1 kilo ohm, I think. Right? So that same thing there. I'm just putting these here. VZ naught was 8 volts, and this was 20 ohms. So at the minimum, when this is 10 volts, I still need 1 milliamp of current here, which means then the voltage difference here will be what? 8 volts plus 0.02, right? This will be 8.02 volts. So what will this current be? Notice again the order of things that I'm doing this in. So you want to follow my the progression on the board. So what is this current there? That's 10 minus 8.02. That's 1.98 divided by 1 kilo ohm. So that's 1.98 milliamps. And please verify that I'm doing correctly. Which means then how much current I have left for this resistor? .98 milliamps, right? This is how much I've got left. If this resistor were to pull any more than 0.98 milliamps, then there wouldn't be enough for that Zener diode. So what condition does this put on the resistor R? Does this tell me what the minimum value of the resistor should be or the maximum value? I want that current not to fall below 0.98. Sorry, not to go above 0.98 milliamps. So does that give me the minimum or maximum of R? I want the current to be higher than that. So I want the resistor to, sorry, I want the current to be lower than that. So I want the resistor to be higher than this, right? So our minimum should be that voltage, which is 8.02 volts divided by 0.98. So, approximately maybe that's what? And that's milliamps, right? So that's approximately maybe 8.1 kilo ohm, right? Approximately. I'm not doing it accurately, right? The resistor should not be smaller than that. If this is a little hard to take in, consider this. Imagine you had a resistor that was 5 kilo ohms in value. Well, at that point, you would require a current going through the resistor that's approximately 8 divided by 5, right? That will take too much of the current that's coming from the top branch, and so your Zener diode will not have enough current. It will go below the knee point, which means then it will leave the mode of operation and go somewhere here, which means then your voltage has changed greatly. That's not a regulated output anymore. Okay? So that's what our min is. And of course, again, you guys will verify what I've done. Let's do our max also on the circuit. And maybe I'll draw it again, just to be. Now, the criterion for R max is that we want to make sure that the Zener current doesn't go above its allowed limit. And that's the risk there is when you have the input being too high. So if you're at 20 volts here, which is the upper limit of the input in this case, you don't want things here to go beyond this point, that 10 milliamps. Okay. So at that point you have, so now for the other end, other side of the limit. So then at that point, what is the voltage here? The voltage drop there would be 8.2 volts, right? So 8.2 volts at that node, if I consider this, will be 8.2 volts. So the current here will be 20 minus 8.2, which is, it's late in the day, what's that? 11.8, right? Divided by 1 kilo ohm, so 11.8 milliamps. And so by KCL, the current I'll have here is 1.8 milliamps. Again, please verify my numbers here. So then R max, 8.2 volts, yeah, 8.2 divided by 1.8 milliamps, which is how much? Is this, say, approximately 5? Yeah, kilo ohms. Take a look at the numbers. So something should bother you. I solved a problem where I got a minimum value of 8 kilo ohm for a resistor and a maximum value of 5 kilo ohm. Something doesn't sound right. So what happened? So here's one suggestion. Should I have solved the problem by saying the risk is the other way around? When the input is too low, when the input is at its lowest, 10 volts, then I should worry about the diode current being too high. And if the input is at its highest, I should be worried about the diode current being too low. Would that solve my problem? That sounds a little counterintuitive, at least. I'm not necessarily saying it's wrong, but let's think about it. Well, you see, again, if you are operating within the regulated region, right, the output is more or less constant, right? More or less. I'm not saying exactly. Of course, we are calculating it, but more or less. So the current going through the 1 kilo ohm resistor is going to be influenced very directly by the variations at the input. So if I double the input, that current is going to go up, right? And in fact, we saw that if I did my numbers correctly, and I trust you guys verified that. We see that we have a much larger current, right? Instead of 1.98 milliamps, we have 11.8. So it's hard to imagine that in the second case, the diode would run the risk of having less current, right? Because that's basically the supply current there. So that doesn't seem to be the answer. So what else can I do to reconcile this? Maybe here's a suggestion for you guys. Do this quickly on your own. Assume that you have a 6 kilo ohm resistor. OK? Put it there. See if you run into any difficulty. What if you had a 6 kilo ohm resistor there? You don't actually need to do the numbers, but look at this circuit. If you have a 6 kilo ohm resistor, it violates your R min, right? It's below R min. And in fact, you would see that if you put 6 kilo ohms there on the green circuit, well, the current going through the green resistor would be more than 0.98 milliamps, right? And that would be taken from that Zener diode, right? So there is a problem. Let's choose something that satisfies R min. Let's take 10 kilo ohms. Okay, let's take 10 kilo ohms. Is there a problem then? Well, let's see. So if you have 10 volts at the top there, and if you try to maintain 1 milliamp through the Zener, you still have the 8.02 volts. If you have 10 kilo ohms for R, then you will get 0.802 milliamps there, right? The Zener current will be a little higher than that, higher than 1 milliamp. And in fact, you would have to recalculate, of course, exactly, because if the Zener current is a little different, the voltage is a little different. I'm not recalculating, right? But I get the feeling that things are going to be OK. Now imagine I keep that 10 kilo ohm resistor. Put it here. When I have 20 volts at the top right, at the top. If I have 10 kilo ohms for R, what happens? Well, let's see. If I have 10 kilo ohm for R, if I had approximately 8.2 volts there, it would give me a current of about 0.8 milliamps, right? What will the Zener current be? Well, if I have 11.8 milliamps going down there and 0.8 goes to the resistor, the Zener current will be about 11 milliamps. That's not allowed. That's bad. If I try to follow one constraint, the other ones seem to be in trouble. What does this say? So what should I change for the first one? Say again? That the idea is not working, yeah? Is that what you're saying? Maybe if I can rephrase this, the circuit is not working as intended, no matter how hard I try. This regulator is not doing its job. The constraints I've given it are a little too difficult. How can I fix things? Suggest one quick fix. Well, maybe think about it this way. The first half I determined R min, right? The problem was when I got an R max that was smaller than R min. How can I change this? You know, how can I be a little nicer on the circuit? Maybe I'm expecting too much. What is it that I'm doing too much of here, maybe? Yeah, maybe I'm expecting too much. I'm saying, you know, I want this wild variation on Vn. And I still want this to work. And it's saying, no, sorry, I can't. It just is not able, assuming I've done the numbers correctly, OK? So you guys go home and verify, OK? But assuming that I did things correctly, if we did things correctly, it seems like this particular diode, you bought the wrong diode. Either you need a diode that can tolerate a lot higher range of variations in current, or your input has to be varying less. This diode can't regulate this range of variations at the input. So, yeah, you know, remember the previous stage that you had built. For instance, it might have been a filtered rectifier. Well, make something that does not have a ripple going between 10 and 20 volts. Okay. If it was between 10 and 11 volts, maybe it would have worked. Alternatively, maybe you need a more forgiving diode. So think about how the different ways in which you might make this work. So I hope this was a little more exciting than just a routine regulator problem, and that it shows what's really happening. So this is R max less than R min. Is this a problem? So I want you guys to think about this. Again, do not consider this problem as solved, okay? I want you guys to verify my numbers and think about whether something went wrong. Think about the two limits and how things would change if I changed any of, if I went beyond any of these limits with the resistor, and if I was in between, right? So just verify my numbers. And then if indeed there is a problem, if we didn't make a mistake here, then how you would fix it. All right? Leave it at that. Thank you.